may want to do here in a second. But here's a little thought process on this. If the problem we run into here with these, I don't know if you're thinking about it or not, but some of these look like, remember the integral of 1 over 1 plus x squared dx? We did that before. That was an inverse trig, right? That was inverse tangent. That one's really nice. However, I don't have that right now. Notice this one's different from that because I've got a square root. And so that complicates things a lot, okay? Because that's a square. Now, if it was just 4 plus x squared, not without the square root on the bottom, got my dx there. We are integrating with respect to x. If it was just 1 over 4 plus x squared, we could do that. We'd have to do a little bit of work, but it could be done with the inverse tangent. But since it's a square root of 4 plus x squared, that's not an inverse tangent. This one might remind you of the integral of 1 over the square root of 1 minus x squared, or 9 minus x squared. If it is even 9 minus x squared square rooted, well, let's do 1 minus x squared because I don't want to. Point is not to do the whole thing through, but that is the inverse sign, but that is not what I have here. Why not? The top is x squared. That's if I have just 1 over the square root of 1 minus x squared. Do I use the inverse sign? You see what I'm saying? These have complications that don't allow us to use the inverse tangent or inverse sign antiderivative. Okay. Not inverse trig antiderivatives. There are some that are, but these aren't. Okay? Sometimes we can get those, but not in this case. Okay. That's where our trig substitution comes in. We're going to use trig substitution on these or ones like these. I don't know if I'm doing the exact same ones here or not, but we are going to use what's called trig substitution. And on trig substitution, we're going to replace binomials and a lot of times they'll be under a square root. By binomials under square root, such as x squared plus a squared minus x squared. The a here is just playing the role of a constant. It could be 2 squared or 3 squared. Or x squared minus a squared. We're going to replace those binomials, such as that, by ultimately a single squared term. That's our goal. And we're going to do that by trig substitution. Let me give you for example. Say we had x squared plus 9 under a square root. We want to replace that. Well, notice this. If I replace the x, actually replace the x by tangent theta. 3 tangent theta. Replace the x by 3 tangent theta. May not make sense why I do that, but maybe we'll get the hang of it here shortly. But replace the x by 3 tangent theta. So, in other words, this right there. So it becomes what? 3 squared, or let's just say 3 tan theta squared plus 9. So it becomes 9 tangent squared theta plus 9. here's why I do this. What can I do to 9 tangent squared plus 9? Factor off a 9. Factor off a 9. And so that becomes tangent squared plus 1 inside there. What's tangent squared plus 1? Secant squared. Yeah, going back to our trig identities there, Pythagorean identities, tangent squared plus 1 is secant squared. And so that's what we're saying. We went with the x squared plus 9, but we replaced it, with a certain thing. And you can see why now we did 3 tangent theta. And it became 9 secant squared, which is, the good thing about it is it's not a binomial anymore. It's just a single squared term. That's what we're saying here. That's what we want to do. So here's what we do. Here's the rule of thumbs for what substitution, trig substitution we make. For x squared, number one, for x squared plus a squared, we've already seen there. So we've got x squared plus a squared. We replace x by what there? We replace x by 3 tan theta. So if it's x squared plus a squared, guess what we replace x by? Well, this was 3 tan theta. So I'm going to go with, this case I went with 3 tan theta, with that because I was squaring it that. So what do I want here x replaced by? Wouldn't it be a tan theta? A tan theta. In other words, the square root of that goes in front. But if it's x squared plus a squared, a tan theta. Now, I could turn that around, it would just be the same. If it's a squared plus x squared, please note you do the same thing, because that's still going to give you 1 plus tangent squared, which gives you still secant squared. Okay? Now, the other two are for the minus. For x squared, a squared minus x squared, so it's a little different binomial. You've got the number squared minus 1 minus x squared first. If that's the case, then you replace x by a sine theta. And we'll see why that is. If you follow it through, like if I have 9 minus x squared, if I replace that by 3 sine theta, which that would give me 9 sine squared theta, that's going to factor off a 9 and give me 1 minus sine squared. And so that becomes cosine squared. 1 minus sine squared is cosine squared. So that's why you do that. And then the third one, well, it turns out if you have x squared minus a squared, it's not sine on that case, it's secant. A secant theta. So those are the 3 we could run into. Now, there's a lot more to it than that, but that's just our first step. So, you with me on that so far? Because here's the other thing. Like we're saying, our integral is going to have the square root of 9 minus x squared somehow involved, just for example. Well, I'm replacing x by 3 sine theta here. And so here's the catch is, ultimately, yeah, I'm going to go with this, and then working it's going to be 9 cosine squared theta, and I'm going to do an integral, but I'm going to be going to thetas, so guess what I have to do? I have to go back to x's, ultimately, right? So let's think about that. What can happen, and what can happen when I do this, when I go back in, let's think about this a little bit. Sometimes I can get integrals, x is 3 sine theta, so that would mean if I get in my answer, it's got something sine theta and then something else, but if I have a sine theta in it, I need to convert that back. So here's what I'm saying. If I have this, x equals 3 sine theta, and my answer has sine theta in it, what is sine theta? Wouldn't sine theta be x over 3? Yeah. Just divide by. Okay. So that's easy. Convert. What if my answer, I'm just hypothetically, what if my answer has something with cosine in it? Well, I know x equals 3 sine theta. What does cosine theta equal? Well, that's where you have to go to our lovely right triangles. Remember, sine is opposite over hypotenuse, SOHCAHTOA. Yeah, we're going to use SOHCAHTOA a little bit, or something like it. X over 3, and so that tells me the opposite is x. So here's theta. So the opposite is x, the hypotenuse is 3. So cosine is going to be whatever this is over 3, isn't it? Adjacent over hypotenuse. So how do I get this one? Pythagorean theorem. Be the square root of 9 minus x squared, wouldn't it? Because this a squared plus b squared equals c squared. And so that would be b squared would be 9 minus x squared. And so b is the square root of 9 minus what we're saying. So a little simple Pythagorean theorem. Okay. So all those things, and there's probably more we'll have to talk about too. Okay. All right. So let's actually do one here. So that's just getting us prepped up here. Okay, you got all these remembered now? All right, good. All right, so I think this was one of our integrals I was talking about. X squared over the square root of 9 minus x squared. Use trig substitution to evaluate this. Okay, so there we've got it. Like we said, you look for the inverse trig antiderivatives, but this one doesn't because of that x squared is complicating things just enough to not be able to do that. And so that's what we're saying then. Yeah, we look for this trig substitution. We're going to trig substitute with the stuff under the square root. So in this case, I've got 9 minus x squared, so I've already mentioned that one. So what do I let, with my trig substitution, I'll let x be something. So 9 minus, so I've got the a squared minus x squared, so that's the sign. The numbers first, and then the minus. It's always the sign, so x is the 3 sine theta. We make that substitution right there. So this becomes x squared. Well, actually, since x is 3 sine theta, isn't that's on top, 9 sine squared, isn't it? Oh, dx. Don't forget dx. Why am I forgetting that today? All right. So x squared is 9 sine squared with me. And then the bottom is the square root of 9 minus 9 sine squared theta. But I'm converting over here to thetas because I want to now do, instead of the derivative, antiderivative integral with respect to x, I want to do integral with respect to theta. So guess what I have to do for dx? I have to convert it to d theta. So that's just like in u substitution. What is dx? Dx would be 3 cosine theta d theta. Not quite like, but yeah. So just do 3 cosine theta d theta. So we've converted all of our x's over to thetas, which that's what's unusual about the trig substitution. What's different about it? Okay? All right, well, like we said, the reason for doing this is because this square root comes out pretty nicely. This is going to be 9 sine squared theta. We factor off 9. So it's 1 minus sine squared underneath that, or times that. So I have 9 sine squared theta. And here's why we ultimately do this. this right here is cosine squared, right? So I have the square root of 9 cosine squared. What is the square root of 9 cosine squared? 3 cosine theta, right? I can square root this now to be 3. I can square root that now to be cosine. With me? Hey, that's going to work out really nicely as far as this step anyway. There's still a little more to do. A lot of work to do. You might want to save a lot of pages for this problem, these problems. But the good news is here, in this case, the 3 cosine theta cancels with the 3 cosine theta. Just leaves me integral of 9 sine squared theta d theta. That's where the fun begins. Because how do I do 9 sine squared theta d theta? I've got it now in a little better form, and I can do this with a little bit of work. How do I do 9 sine squared theta? Huh? I'm going to have to use the double angle. Yeah, I've got a trig integral here now. And it's there's no odd sine or cosine. That's the double angle. And the double angle, sine squared is, it's 1/2 times 1 minus cosine 2 theta. Isn't that what it is? And so this becomes the integral of 9. So I make the sine squared, it's going to be, well, it's going to be 1/2 minus 1/2 cosine 2 theta. I will go ahead and multiply the 9 in 2, so I get integral of 9/2 minus 9/2 cosine 2 theta, d theta. All right. We can do this, though, right? This is then just 2 integrals. It's the integral of 9/2 d theta. And this is minus the integral of 9/2 cosine 2 theta d theta. I'm splitting that out because there's still a little more work on this one. A little u substitution, isn't it? Simple substitution. U is 2 theta, du is 2 d theta. So du over 2. Okay, so this is 9/2 theta minus, well, that'd be 9/2 cosine u times d theta is du over 2. Yeah, now it's just, well, it's 9/4 the cosine du, so we're in good shape. Antiderivative. Be 9/4, the antiderivative cosine is sine. And u is 2 theta, so I'm going to go ahead and do that. With me? Plus c. Which almost looks like we're done, but not quite. Doesn't look like we're done. Why aren't we done? We've got to put it back to x. Okay. Got to put it back to x. That's where we go back to this. Go back to your original substitution, x equals 3 sine theta, and draw a right triangle. Well, it'll be x over 3 is sine theta. And I don't have a lot of room, but so I'll go right here. So I know x over 3 is sine theta. Well, one thing I need to know is what theta is. And if I do the right triangle, I can figure out an expression I can go with for, well, I don't even have to do that. If here's just wanting theta. So if x over 3 is sine theta, what would theta be? Well, if x over 3 is sine theta, wouldn't theta be the inverse sine of x over 3? I'm wanting to know this angle, right? Theta for this?
Oh, so you're just switching line angles.
Yeah. Yeah. It's just sine inverse. Okay, so that's going to go in for theta. Sine inverse x over 3. 9/2 sine inverse x over 3. Now, this one's Fun also. Fun also. Not too bad, though. Sine of 2 theta. Notice there, that's sine of 2 theta, not sine of theta. Well, I need to get it back to sine of theta. And actually, it'll be cosine theta. There's another double angle. You know, we were using the cosine double angles, but the sine double angle, isn't the sine of 2x equal to something? 2 sine x cosine of x, yes. So if I have sine of 2x, I can convert that over to sines and cosines. It's just 2 sine of x cosine of x. Remember your trig identities. Whoops, theta. Not x now, it's theta. All right, so now we're getting somewhere. That's why we're almost there. That's why I drew the little triangle here. If sine of theta is x over 3, that means this is x, this is 3, right? So this would be the square root of 9 minus x squared. We just did that just a second ago. And the reason I need to do that is because I need both the sine of theta, which is x over 3, and I need the cosine of theta, which is, what would cosine of theta be then? Well, cosine of theta is the adjacent over hypotenuse. So that's the square root of 9 minus x squared over 3. So I replace cosine by that, sine by that. And I've got it. 9/2 sine inverse x over 3 minus 9/2 sine is x over 3. Cosine is the square root of 9 minus x squared over 3 plus c. And the good news is this 3 and this 3 cancels that 9. So my final answer is 9/2 sine inverse x over 3